At dusk, a red rubber ball rolls across a lawn. The dog beside you snaps its head toward the movement, races after it, and then slows down near the shadow of a hedge. You might assume you know why. Dogs are colorblind. The ball is basically gray. End of story. Except that story is too simple in almost every direction. Dogs do not see the world in black and white. They can use color information. They can notice some flicker that many humans smooth into a steady image. In low light, their eyes can gather light in ways ours cannot. And yet, when the task is to resolve fine detail, a human usually has the advantage. It is what happens when you stop asking one vague question, what does a dog see, and start asking several smaller ones. What colors can it tell apart? How much detail can it resolve? What changes when the light falls? How quickly can it detect a flickering signal? And how much do those answers change from one dog to another? The familiar black and white claim began with a real difference. Human color vision usually uses three kinds of cone photoreceptors. Cones are cells that respond best in brighter light and help distinguish wavelengths. Dogs have two main cone pigment classes instead. In behavioral color tests, researchers found sensitivities with peaks near 429 and 555 nanometers. That is strong evidence for dichromacy, a two-channel color system, not no color system. But two channels do not hand us a translation dictionary. It's tempting to say dogs see blue and yellow, because those labels can be useful shorthand for how their discriminations differ from ours. The problem is that blue and yellow are also names for human experiences. A pigment sensitivity peak tells us which light a receptor responds to most strongly. A discrimination test tells us that a dog can make one choice rather than another. Neither one lets us borrow a dog's point of view and inspect the color itself from the inside. What the experiments show is more interesting than the myth. In one study, dogs had to choose between stimuli that differed in both brightness and color. Brightness was available as a clue, yet the dogs generally used the chromatic difference, the color information. So color is not decorative noise in a dog's visual system. Under those daylight-like test conditions, it can guide behavior. That doesn't mean a red toy has a stable, obvious identity for every dog on every lawn. Color is only one clue. The brightness of the object, the background, the direction of light, its smell, its motion, and the dog's past experience can all change the problem. Near sunset, color information weakens as the light weakens. The question becomes less like, what shade is that? And more like, is there enough contrast to find it? This is where the next popular number appears. 2075. If a dog is described as having 2075 vision, the comparison means that detail a person with normal 20/20 vision could resolve from 75 feet away might require the dog to be about 20 feet away to resolve. The number came from a review that gathered very different ways of measuring dog vision, trained behavior, electrical responses from the retina or brain, and reflexes to moving patterns. The review itself warned that the estimates varied widely before treating 2075 as a rough typical value. That caveat matters because acuity is not simply whether a dog can see an object, it's the ability to separate fine lines or small details under a particular test. Later work made the variability impossible to ignore. In a two-choice experiment, dogs had to choose between horizontal and vertical stripe patterns. Under bright light, the tested dogs ranged from 5.5 to 19.5 cycles per degree, a measure of how tightly packed the stripes could be before the pattern became too fine to discriminate. Under dim light, the range dropped to 1.8 to 3.5. The final sample wasn't every kind of dog. It was 4 Whippets, 1 Pug, and 1 Shetland Sheepdog. A single Snellen-style number can be a starting place, but it cannot be the last word. Even the eye itself refuses to be one thing. In many dogs, the retina has a horizontal band with a relatively high density of ganglion cells, the neurons that carry visual signals toward the brain. It's called a visual streak. Think of it as a strip of retina organized to sample a broad horizontal scene. In other dogs, the emphasis can shift toward an area centralis, a smaller region of especially high cell density. Studies of dogs' retinas found that this distribution varies with skull shape. Longer-snouted dogs tend, in the studied samples, toward a more pronounced visual streak. Shorter-snouted dogs can show a more pronounced area centralis. The correlation is striking, but it's not a personality test disguised as anatomy. It doesn't prove that one individual will always see better, notice movement sooner, or succeed at a particular job. The optics of the eye, age, health, training, and the task in front of the dog also matter. Still, the anatomy gives us a reason to abandon the idea that every dog carries the same visual map. People often say dogs are built for movement, as if that settles everything. There's a grain of evidence behind the phrase. Dog retinas are rod-dominated. Rods are photoreceptors that work well in low light and contribute strongly to detecting contrast and change. The canine eye also has a tapetum lucidum, a reflective layer behind part of the retina. Light that passes through the photoreceptors can be reflected back for another chance to be captured. That's why dog eyes can shine in headlights. The advantage is not magic night vision. Reflection can scatter light, which may blur fine detail, and a retina that's good at detecting a moving shape is not automatically better at every kind of motion problem. A dog following a ball, a dog separating stripes, and a dog recognizing a shape on a screen are not taking the same visual test. Flicker makes that distinction especially clear. Critical flicker fusion frequency is the point at which a rapidly blinking light stops looking like separate flashes and seems steady. In a behavioral experiment, 4 trained beagles could detect flicker in a range reported around 70 to above 80 Hz, depending on the stimulus conditions. That's often higher than the threshold quoted for many human observers. It's a real difference in temporal sensitivity, but it's not a universal frames per second for dogs. Flicker thresholds change with brightness, wavelength, contrast, and method. A screen's refresh rate is not the same thing as the way its light is modulated, and seeing a flicker is not the same as possessing universal superior motion perception. The careful conclusion is narrower. Some dogs, in a particular kind of laboratory task, could distinguish rapid light fluctuations that a slower visual system might blend together. That narrow conclusion isn't disappointing. It's a better question. When a dog pauses over the red ball, the pause may not be a failure of vision at all. It may be a shift in which clues are reliable. In brighter light, color can contribute. In lower light, rods and contrast become more important. Motion can make the ball easier to localize than a still object. The dog's retinal layout may favor one region of the scene over another, and none of those statements requires inventing an inner picture with human labels pasted onto it. This is where dog vision filters become misleading. A filter can remove certain colors, lower apparent sharpness, or add a greenish glow. It can be useful as a teaching model if it clearly states what variable it represents, but it's not an answer to the question in the title. It can't include the dog's retinal topology, its optics, the exact lighting, its behavior, and what the signals mean to that individual animal. Most importantly, it cannot reveal qualia, the technical word for the felt side of perception, not the wavelength measured by a device, not the choice recorded by an experimenter, the actual appearance of a color, the lived quality of a shadow, whatever it is for the experiencing subject. Science can map the receptors and test the choices. It can build increasingly good models of what information is available. It cannot place us inside a dog and let us verify the private feel of that information. That limit should make us more careful, not less curious. We don't need to pretend that a dog sees our reds as our reds in order to take its visual world seriously. We also don't need to flatten that world into gray because it's different from ours. So the next time the ball rolls into the evening grass, notice what the moment actually contains: a moving object, a changing light level, a 2-cone color system, a rod-rich retina, a reflective layer, a particular skull, a particular eye, and a particular animal making a decision with information we can measure from the outside. The old claim says dogs see less. The evidence says something more demanding. They see differently, not uniformly, and never in a way we can completely translate.